might want to try going to church and see what they do. So, you know. All right, so yeah, so again, kinetics deals with how fast the reaction occurs. Okay, well, what impacts? So what can change the rate of the reaction? Okay, so how can you make the reaction go fast or slow, whatever? Okay, but now thermodynamics of the reaction deals with what? If this reaction will occur or not. Okay, so like remember guys, like AB Bio, right? Like so, is what like spontaneity. Spontaneity of the reaction, right? Like okay, so is a reaction spontaneous or not? Okay, so what decides spontaneity, guys? AB Bio, what do you think? Delta G. The Gibbs free energy value, change in free energy. Okay, if this guy is negative, it's what? Oh yeah, that's a spontaneous reaction. If delta G is positive, it's a non-spontaneous reaction. That's something that you've probably seen from the AB Bio, right? So, you know, endergonic, exergonic, you know, blah blah blah. So if delta G is negative, oh yeah, that reaction is what? Oh, it's a spontaneous reaction. Okay, like yeah, that's the next chapter. That's what it was, right? Which means what? The reaction will occur. Okay, so like remember guys, like ATP turns into an ADP and phosphate. Okay, so like this one makes a reaction, even though a reaction A turns into a B, even though the reaction might be like, you know, non-spontaneous delta G positive, but ATP helped them out to make the overall process be negative and the reaction will occur, blah, blah, blah. That's the energy, like, you know, like energy of the reaction, blah, blah, blah for the bio, right? So, you know, and it's just about the same thing for chem, based on spontaneity, okay? Is the reaction happening or not? So that's what this is. So spontaneity of the reaction depends on other factors, such as, you know, is it the entropy of the reaction, enthalpy of the reaction? That's what this is, okay? So enthalpy and entropy will decide the spontaneity. Okay, so the equation is delta G is equal to delta H minus T times delta S. So there will be an extensive chapter on this one, by the way. So this is like very towards the end of the chemistry, by the way. Okay, so second semester. Delta H and delta S, change in enthalpy, change in entropy, this will decide ultimately what? The delta G value, which is what? Like, yeah, the spontaneity, would the reaction happen or not? You look at these two values, okay? So enthalpy and entropy, so heat of the reaction, like endothermic, exothermic, and what? Entropy. So I don't want to talk about it right now. So, but kinetics deals with completely different stuff, okay? This is like, okay, so reaction can be spontaneous reaction. Okay, some of the reaction that you already know, spontaneous reaction, right? So what's an example of spontaneous reaction, guys? If I have a you know, like so I like okay, so there's a at home, right? Like so, like I think my mom complained. She bought like a new the mixer, okay, to mix like fruits and stuff, whatever, okay. She looked at the bottom of the mixer. She complained to me that it's like she used it for about a year. She noticed the screws were rusted, okay, like rusting. So rusting, guys, by the way, okay, is what? It's a spontaneous reaction. Okay, you have a piece of iron, right, reacting with the O2 gas and what turns into iron oxide. So that's a rusting. Okay, that's like, dude, that is what? That is basically what we call, guys, a spontaneous process, okay? But now, okay, so yeah, delta G is negative, blah, 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 whatever, okay? But now, which is what, yeah, like, but does that mean, so like, so that it was meant to happen, the rusting is meant to happen, but now, how do you make it happen faster or slower is what? That's kinetics, okay? So how do you make the reaction rusting happen faster? How do you slow it down? Whatever is what? Deals with the kinetics here. So this will tell you whether this will happen or not. This will tell you what, guys, how fast the reaction occurs. So now, you should like have heard, like, you know, for the regular chemistry classes, guys, not AP, you should have heard this, because how do you make the reaction go faster? How do you make it go faster? So you want the reaction to be happening faster. What the hell do you do, guys? So there are a few things you've probably heard already. You should already know this, which is what? Temperature. Increase temperature. Temperature go up, right? Dude, like no question, right? If you increase temperature, the reaction will happen faster. Okay, that's one. All right, what else, guys? Also what? Concentration. Increase concentration. Okay, that will make the reaction go faster. Okay? And also, you probably heard, guys, surface area. If you increase surface area of the reaction, okay, surface area of the reactant, the reaction will happen faster. Okay? And what else, guys? So, okay, so what else, guys? It's what? Catalyst. or like, you know, probably you like kind of heard from bio, like enzymes maybe, guys, by the way. So these things, okay, temperature, concentration, surface area, and catalyst, these are what, guys? These will what? These are the ones that can possibly change the rate of a reaction. Okay? So at most, for your chemistry class, whatever you took last year, okay, they probably talked about like a few things here. Okay, like, oh yeah, this is how it increase, how it goes down, and stuff like that. So temperature, when temperature goes up, what happens, guys? So how can increasing temperature, you know, assist or help the reaction to happen faster? Temperature goes up, what happens, guys? They what? Kinetic energy goes up. They move faster. Okay, they start to move faster. If they move faster, what happens, guys? Yeah, like dude, like the collisions, right? So kinetics is all about collisions, like collision, like it's a collision theory. Okay, collision theory. So which means like, okay, so in order for the reaction to occur, they have to collide. They have to collide for the reaction to happen, right? So which means, okay, so if they have enough kinetic energy, which means what, guys? Yeah, they have a better chance of what? Overcoming the energy of activation. So they have to have this much energy to what? For the reactions to occur, right? But if you have a greater energy when they collide, what happens, guys? Yeah, like dude, what happens, guys? Yeah, so which means what? Yeah, a lot of the particles have more energy to collide, and more energy when they collide, and what? Overcome the energy of activation. Okay. So what it means is, it changes what increases. What increases? Effectiveness. Okay, effectiveness of the collision. Okay, so effectiveness is what, guys? Like, so I mean, so if you guys watch like sports, like NBA, okay, so like, oh yeah, there's this player's effective. Like, oh yeah, they're very like efficient and effective. What does it mean, guys? Yeah, dude, it means, for example, guys, what? Okay, so it means out of like 10 collisions, maybe there's what, like 7 reactions, for example. Out of 10 collisions, 7 of them turns into reaction. While at a lower temperature, what happens, guys? It'd be like more like 2. So that means what? If this number goes up, out of 10 collisions, like, you know, the number of collision occurs, number of reaction occurs, increase. That's what we call it. Effectiveness goes up. Okay, that's basically the first thing that occurs with temperature going up, right? And also what happens, guys? They move faster, just like how the pressure goes up, is what the frequency goes up. Frequency of the collision goes up. Which means it was 10 collisions per second back like, you know, before temperature going up. Is what now it's like 15 collisions per second. The frequency went up. Okay. So, you know, when temperature goes up, because they move faster, effectiveness and the frequency of the collision goes up. This is AP. Okay, dude, I'm not kidding, guys. They'll ask you, okay, when temperature goes up, okay, explain 2 ways to what? How the rate of the reaction goes up. You gotta write what? Effectiveness and the frequency of the collision. Okay, you gotta explain it. That's one way. That's not something new. You already know that. Okay. Concentration. So concentration. So this is something, guys, that you know, something that they'll be asking. Okay. Concentration is what, guys? Like molarity. Okay. So meaning, guys, molarity is basically the measurements of concentration, guys, okay, which is what? Number of moles divided by the volume. So concentration is what, guys? If you have a high concentration, which means what? You have a greater amount of reactants per given volume, okay? Which means like they're really packed in, like they're like, you know, packed in together. So, for example, guys, I mean, so at a high concentration where the particles are like you know, the reactants are not far away from each other, guys, what happens, guys? There's a greater chance for collisions, okay? So, yeah, dude. At a higher concentration, what do you mean by that? Yeah, they are more likely to what? Collide. Okay. So if the concentration goes up, what happens, guys? The frequency of the collision goes up. Okay, but not the effectiveness. So which means there's more collisions between the particles. So by increasing concentration, there's a greater chance for what? The frequency of the collision to go up, which is rate of the reaction will go up. And surface area, like, I mean, this is like kind of really easy, guys, by the way. So surface area is what, guys? Yeah, like if you increase surface area of the, you know, the reactant, what happens, guys? The rate of the reaction will go up, right? So, for example, guys, if you want to cool down your beverage, right, then you have an option, right? Would you use shaved ice versus like block of ice? Which one will cool down faster? Of course, shaved ice, right? So something like that will be explained by the surface area. Okay, nothing fancy. And catalyst. So catalyst, I mean, so in your bio, it was an enzyme, but enzyme is a completely different ballgame for this, okay? Enzyme is a protein, but catalyst in bio, I mean, in chemistry, I'm sorry, can be what? Can be a single atom, like chlorine, for example. A single atom can be a catalyst, okay? So you gotta understand, guys, catalyst, I mean, dude, like, so you don't have to be like super smart to figure it out, guys, right? It, like, one thing that you know is what? It lowers the energy of activation, okay? Like, again, would that be enough for AP Chem, guys? No. So catalyst, keep in mind, guys, is what, guys? It provides a different pathway for the reaction, okay? So it used to be A turns into B, but now what happens, guys? It gives you a different pathway, different road to the product, okay? So that's what catalyst is, by the way, which will change the energy of activation. But now, so these four things will have impact on kinetics of the reaction, okay? So thermodynamics was all what? Enthalpy and what? Entropy. That's what will have an impact on the spontaneity, whether the reaction happens or not. But now, kinetics of what, guys? These things. That's something that you should already know, okay? This is something that you should already discuss in your regular chem class, okay? So whatever the chem you took, by the way, okay? But what's different with AP is what? You have to put this in a formula, okay? It's not like, okay, next chapter. No, you gotta explain this in a formula, okay? So these are the ones that have an impact on the rate of reaction. These are the ones that can change the rate of reaction, okay? But now, you have to put this in an equation and solve questions based on this. The equation is this. This is what they call, guys, differential rate law, okay? It sounds very fancy, but it's not. Listen very carefully now, okay? It's called, I'm not gonna write it, okay, differential rate law. So where you give a reaction, A turns into B. That's a reaction, okay? There's a reaction, so you know what? Let me see. A plus B turns into C, okay, whatever. So that's a reaction right now. A and B react and turns into C. So let's write something we call differential rate law, which can have an impact on the rate, okay? The rate is equal to the rate constant K. K is a rate constant, okay? Times concentration of A times concentration of B, okay? This is what they call, guys, okay? Differential rate law, okay? So what they will ask you is coming up with this equation first, okay? Like they will ask you, oh yeah, by the way, you know, can you get a differential equation for this reaction? That's one of the questions they'd be asking, okay? It's one question. And then like they'd be asking, okay, so if you know the concentration, okay, of the reactant, okay, if you know the K stands for, guys, this is what we call the rate constant. Okay. So that's what, so if you know rate constant, if you know the concentration, then you can figure out the rate of the reaction, okay? But you gotta understand, like a lot of the schools, they just like teach, like whatever, like solve question, next chapter. You gotta understand, guys, differential rate law, okay? You gotta understand what the hell this means, okay? So these are included in the rate law, okay? Keep in mind, guys, by the way, so whatever that's included in the rate law, differential rate law, right? These are what? They can alter the rate of reaction. So what I'm saying is, whatever that can change the rate of a reaction should be included in the differential rate law. If something can change the rate of the reaction, this must be included in the rate law, okay? But now, okay, what about the stuff we just talked about? Temperature, okay? Concentration, okay? And what? Surface area. Also what, guys? Catalyst. So, I mean, concentration of the reactant is in there, okay? Which, yeah, check. But what about temperature, surface area, and catalyst? What about those guys? Where are they at? It's in what? It's in the rate constant. So, which means, guys, the rate constant K has a lot more in it than what is. It's not just a constant. It's a little more than that, okay? So, rate constant K, this is what they call, I'm telling you, you gotta know this, by the way. So this is something, if there is something you don't have to know, guys, I'll tell you, okay? This is something you have to know. K is a rate constant, but they're based on Arrhenius equation. You have to understand what's in here. K is equal to A times, okay? A is not like this, okay? It's completely different, okay? E to the power of negative of the energy of activation over RT. That's the equation for rate constant. This is called the Arrhenius equation, okay? Like, put your phones away. So this is what, guys? So, like, you gotta understand what this is and what these are. Okay. So A, energy of activation, and temperature. So this R value is what, guys? The same R value for the PV and RT equation. Same R, okay? That's the equation. Okay. So now, okay, so so look at it, guys. Catalysts will change the energy of activation right here. Okay. So right there, energy of activation, guys, by the way. Okay. So now if you lower the energy of activation, like K value goes up, which means rate will go up. Okay, so basically, this one will have everything in there, right? Temperature. If you increase temperature, K value is going to go up, rate is going to go up. So everything that can have an impact on the rate, whatever that can change the rate is in the equation. Okay. And now this rate right here, A is what we call, guys, the collision factor. Collision factor deals with surface area as well. Okay, so which means what? So if surface area changes, then A changes. Okay, which means K will change based on that, guys, which is the rate. So whatever that we talked about, whatever that can change the rate, guys, can be what? Yeah, dude, it's in the rate law. Okay, so that's what differential rate law is. Okay, whatever have an impact on the rate should be included in there. Okay, including all the stuff we talked about. So the difference with what you learned, I mean, hopefully what you learned in your kinetics that your school teacher taught you versus AP is what? So it was very qualitative what you probably learned. Oh yeah, like this is it. Okay, next chapter, you gotta calculate that. Okay, the rate will be calculated and it will have to be discussed. Okay, so you definitely have to. I tell you guys, your teacher might not talk about this equation, guys. Absolutely no question you have to know this, guys. You know, this is something that you have to memorize and know what it is. So let's take a look, guys. Okay, so first thing first, guys. Okay, so before like really getting too crazy with this, okay, how do you calculate, okay, a rate of a reaction? How do you calculate this? I mean, so like rate is okay. How do you measure a rate of reaction? So like, okay, so we talked about rate of reaction, right? How do you measure this? Are you looking at your phone right now, or what? You want to break that phone? I told you, right? Like, dude. Oh gosh. All right, so imagine what I mean, this is remote, man. Like, I don't know, dude. I tell you, like, the reason why I'm not doing remote is like something like that. I mean, you can do freaking all day. I do not know. All right, so how do you do the rate? How do you calculate the rate, guys? What do you measure rate? Is what? So A and B, or what, guys? A and B are getting consumed. Okay, they're being consumed turns into product. Okay, which means what? Like, yeah, dude. Which means, I mean, you have, for example, guys, some of A, some of B, which means what? They will be consumed. They're going away. They're being diminished in concentration, right? So rate can be calculated by what, guys? Changes of the concentration of A over time, right? So how fast A is going away. So, dude, like if this is a fast reaction, what's going on, guys? This is what, dude, this is rate. This is how you measure a rate of reaction. So A and B is being consumed. Okay, yeah, dude, okay, so measure the changes of the concentration of A, which is reacting what, over a given amount of time, is what? That will measure what? The rate of reaction. So yeah, like, dude, okay, that's one of the ways to do it, right? So if, for example, guys, okay, yeah, so it was 1 molar concentration, went down to 0.5, okay, in 1 second, okay? It went down from 1 to 0.5 in 1 second, okay, which is what? This is what, okay, so I have a 0.5 changes over what, 1 second, which is what? 0.5 molarity per second. That's the rate. So which means a lot of times the rate is measured as what? Molarity per second. That's basically, guys, what we call the rate of reaction. Okay, how fast they get consumed. And now, yeah, B, right? Okay, so B, you look at it, guys, B, okay, so which means like this is a 1-to-1 ratio. If this is how fast they go, probably the same, you know, as for B as well, guys, by the way, so, and for C as well, okay, how fast like these get consumed and this gets produced, okay? So that's one of the ways, I mean, that's one of the ways you can calculate what? The rate of reaction, how fast they go, how fast they create, okay? So one of the question on the AP, okay, like this is being asked on the AP, and also this is, I don't know, I'm not sure, okay? Probably asked on your like Olympia Chem, you know. It sounds very simple, but it's a very simple mathematical equation, okay? So 2A, for example, I have a separate equation, 2A plus B turns into 3C. That's a reaction. For example, that's a reaction, okay? And now, so what the question is asking, okay, the rate. So from here, like the students like who are not like very math like oriented, they start to like, like, oh my god, what the hell. So rate, right now, I'm gonna use A, concentration of A for the rate. Rate is for the guys, concentration of A, delta over delta T. Okay, changes of the concentration of A over change in time. So that's basically, guys, what I'm gonna measure as a rate of reaction. Okay, whatever it is. So it's a number. It's a number, right? So I have some A, I have some B, some C gets created, guys, by the way. So now, how is, like, the rate is a number, right? We're gonna have like 3 molarity per second, whatever that is. But now, like, okay, so what the question will be asking, like, dude, I'm not getting it. Like, very unlikely. I mean, so I've seen this question on the AP, okay, and they always ask this question on the Olympiad of chemistry as well. I mean, it depends on the school test. I mean, it depends on how, like, well advanced the school teacher is and what kind of question they give you, by the way. But now, they want you to express, so this is what the question is, okay? They want you to express the same rate using B or C. You understand what I'm saying out here? They want to use B or C. So meaning, okay, so express the same rate using changes of the concentration of B. That's what they're asking. So, okay, so I have a 3 molarity per second as a rate, okay, for the reaction, okay, right now. But now express the rate, okay, using changes of the concentration of B. Okay, that's what they're asking. Dude, I'm not kidding. So, okay, so take a look at this, okay? So changes of concentration of B over delta T. Okay, so like, is it equal right now, we think? No, they're not. The rate of A being consumed and B getting consumed, but they're not the same. So, yeah, right now, A getting consumed is what? Like 3 molarity per second, okay? Based on what we know. What will be the rate of consumption for B? What do you think? Like, it's 2 to 1 ratio. If you have 2, you got 1 there. Do you understand, guys? If this is 3 right now, this is what? This will be what? 1.5. You understand what I'm saying? Because as 2 goes away, only 1 goes away. Do you understand what I'm saying? So how do you make it equal? What do you do, guys? What do you have to do? You got to multiply this by what? 2. Do you understand what I'm saying? So this is basically what they ask you. Okay, so express the same rate using the concentration of B. Which is, oh yeah, I got a delta B over delta T, multiply that number by 2, then you can say, well, they're equal. Do you understand what I'm saying here? So now, my question to you guys is this. Express the same rate using the concentration of C now. Okay, that's something, write it down, guys. Right? Express the same rate using C. Okay? It's like, right? Like, I need like something, okay? So delta change in C over delta T. Okay, I need like some kind of number here, whatever. In 2 seconds, guys. In like a couple minutes. This is math, okay? Let's just know. Okay, so if you look at, I mean, again, if you look at, I don't have much time. So if you look at this, guys, so if 3 goes away, so this is 2 to a 3 ratio, right? You understand? Like if 2 goes away, 3 gets produced, okay, which means what? Okay, so if that's the rate, this is what it is right now, it's a 2 to 1 ratio, 3 will split, this is 4.5. So this would be what? Like delta C over delta T is what? 4.5, right? You know, it's what? It's a greater, it gets produced at a greater rate, and how much of the A gets consumed. Okay, so how do you make it equal, guys? What do you have to do? It's what? So to make it equal, what do you have to do, guys? I think you have to do, it's like 2 over 3. You gotta multiply by a small number, 2 over 3. So is this right, guys? Do you think, what do you think? Is this right, guys? 2 over 3? Times that number, right? So it's ratio is 2 over 3, so 3, like, is it right, guys? Keep in mind, guys, okay? if you write it like this, it's incorrect. I mean, so I don't know about your school test, guys, by the way. AP, this is pushing it. But now, keep in mind, delta means what, guys? Product minus reactant, okay? These are getting consumed while they're producing. Okay, which means what? I gotta put what? Minus sign there. Okay, so you know, so minus sign. So if these are, if I put this as positives, this must be negative. So yeah, because what? They're getting produced while these are getting consumed. Okay, so you know, but that's something. Again, I can't like give you a question right now. Solve this. Again, that is something that's in scope that AP is asking. Okay, so you know, where so based on a reaction, can you express the rate in terms of a changing concentration over time based on the reactant product based on their coefficient as well. Okay. Any questions there, guys? So now, the other part of the stuff that you have to know is coming up, or they'll be asking, okay, determining the rate law of the reaction. So they give you this. They give this reaction, right? And they'll be asking, okay, write the rate law for this reaction. Okay, so like, let's say I'm going to give you this. Okay, 2A, 1, like a 3C. Okay, that's a reaction right now, okay? So as I mentioned to you guys, okay, so make sure you understand what I'm saying. So you might, oh yeah, my God, you know, is the rate equal to K times, so can I just, like, can I figure this out by this? Like, K times A to the power of 2, B to the power of 1. So should the coefficients be always exponent, guys? That is wrong. You can't do this. Yeah, so the coefficients are not exponent every time. That is incorrect, okay? So to determine the rate law, you need either one or the other that I'm going to mention, okay? One of them is, you need two things. You need one or the other from what I mentioned here, okay? One is the mechanism of reaction. The mechanism of the reaction. So what I mean by that is this, okay? So so we talked about this, guys. Kinetics is what? Based on collision theory, okay? They're based on collisions. Which means, guys, okay? Like, look at what the reaction is right now. They're saying 2A and 1B are coming together, reacting, and what turns into what? 3C. Okay? So, like, let me tell you something, okay? For a reaction, two things colliding and then turns into a reaction is not easy, okay? Like, think about two things colliding with the right orientation, the right energy, turns into a product. That is not easy, okay? But imagine three things colliding at once turns into a product. What do you think, guys? Do you think this is likely, guys? What do you think? So imagine, guys, you guys go to a mall, okay? You guys like seeing like your longtime friend that you never met before, okay, for a long time, okay, during like before COVID, whatever, okay? So it's rare to see someone. I mean, unless you're like really popular. I don't know, you know. So, you know, it's not. It's like I'm not. So if I go to the mall, I rarely see like my friends, okay? But what are the chances to meet two of your friends? They're not together, and like bumping into them two at the same time? Very unlikely. That's what's happening right now. So three particles coming at once and turns into reaction, not gonna happen. So which means what, guys? Typically reactions like this result in what? Multiple steps of the reaction. So it's just like this, right? So okay, so A plus A turns into X, for example, okay? So A and A is gonna react first, turns into X. And X is gonna react with B, turns into what, guys? Product, which is 3C. So it's what? Typically what, two-step reaction like this, okay? But if you add it, what happens, guys? Yeah, it turns into what? It turns into this. So, we don't know, okay? So unless they tell you what the mechanism is, we don't know, okay? So yeah, what do we call X here? X here, what do we call X here? X is what we call as what? Intermediate, okay? It's something that was produced in the step and gets consumed in the step. That's called intermediate. Intermediates are not in the rate equation, by the way, or the equation overall. So now, okay, so I have two steps here, okay? And now, listen very carefully. This is the slow step. This is a fast step. Okay, this is a slow reaction, that's a fast reaction, okay? This reaction is really slow. This is very fast reaction. If there's X and B, like right away, 3C gets created, okay? So now, in a reaction like this, okay, there is something they call, okay? Now this is what we call, guys, mechanism of the reaction, by the way. Okay, there's something we call, guys, the rate determining step. Okay, so there are many steps of the reaction. Okay, which step determines the rate of reaction? What do you think? So I mean, this is a super fast. That's really slow. What do you think, guys? Slow step is what? The slowest step of the reaction is what? They are the rate determining step. Because what, like, dude, it doesn't matter how fast this is. If this reaction does not happen, what happens, guys? Dude, this is not going to happen. Okay, so the rate determining step is what? The slow reaction. So mark by word, just so you know. So yeah, what does it mean? Yeah, what does it mean, guys? Doesn't matter if I add more B in the reaction. So okay, so this is what it is, right? If I add more B, okay, does that change the rate of the reaction or not? What do you think? It doesn't, because why? This is slow, which means what? Okay, so if I add more B, it doesn't really change the rate of reaction. Because why? What slows it down is what? Is the first step. So, which means what? The concentration of A have an impact on what? The rate of reaction. It doesn't matter how much B I added. As long as there's something there, this will not have an impact on the rate at all. Do you know what I'm saying? So remember, guys, listen very carefully now. Listen very carefully. This is where the students really struggle to understand. Yeah, differential rate law equation is a lot of times what the rate law is, right? Okay, so they're gonna ask you based on the mechanism, okay? They're gonna ask you write the rate law for this reaction, okay? So which is what? Okay, so rate law is what? Rate is equal to K times concentration of A times the concentration of B. Those are reactants, right? But now, keep in mind, again, what gets into the differential rate law is what? What can change, what has impact on what? The rate of reaction. So whatever that can change the rate of a reaction must be included in the rate law. If they're not, they should not be present in the reaction. So look at this, guys. We look at it, guys, we understand A have an impact on the rate law. B, it doesn't. Because it's not included in the rate limiting step. This is a rate limiting step, right? Which means what, guys? For B, the exponent should be 0, because why? B is not included in the rate law step. But now what about A to the power of 2? So this becomes what we call the differential rate law for this reaction. So rate is equal to K times concentration of what? A to the power of 2. That's the rate law for the reaction based on the mechanism I provide to you. Okay? So now, why is it A to the power of 2? Because why? There are 2. Okay, there are 2. Like if I rewrite this is what it looks like. 2A turns into X. Okay, so that 2 becomes what? Exponent. Right there. Okay? For the rate for the mechanism, okay, the exponent can be the coefficient. Okay? And this becomes a rate law right there. Okay, so yeah, then B is not there. So yeah, listen carefully. This is where the students are really like I don't know, they're very puzzled. So they see the rate law. Okay, they look at the rate law. Okay, what? Oh yeah, B is not there, which means what? This is the big problem. Okay, they think B does not participate in a reaction. That's what oh yeah, B is not there, which means B doesn't react. That's what they think. Make sure I'm saying, guys. The rate law tells you what, guys? What can change the rate of reaction? B is not there because what? B does not participate in a rate determining step. Concentration of B does not change the rate of reaction. That's the reason why they're not in there. It doesn't mean that B doesn't react. That's one of the key things to understand, guys, based on the rate determining step and also the differential rate law. So, guys, I gotta let you guys go, but I gotta go too. So there's more to talk about in this chapter, so you know. So I think for your homework, guys, like just look at me. So I can So it doesn't matter if I assign you homework or not, but I'll assign you the reading for this chapter, and we'll discuss further on this one. And then next week, guys, we'll discuss kinetics, and then like the stoichiometry, and that's it. Okay. All right, guys.